When we write a number in decimal notation, we're expressing a number by expressing how many copies of each power of 10 are in the number. For example, 375 is the number that's equal to 3 copies of 10 squared plus 7 copies of 10 to the first plus 5 copies of 10 to the 0. This extends to negative powers of 10 also, which enables us to express numbers that aren't whole. For example, 375.2 equals 3 times 10 squared plus 7 times 10 to the first plus 5 times 10 to the 0 plus 2 times 10 to the negative 1. Another example is 1/7, which equals 0.142857142857. That pattern continues with the initial string of 6 digits repeating without end. We can write 1/7 like this as a sum of copies of negative powers of 10 that never ends. But how do we make sense of those 3 dots at the end? What does it mean to add infinitely many numbers together? The nth partial sum of a sequence A sub n, denoted by S sub n, is the sum of the first n terms of the sequence. For example, the 4th partial sum of this sequence is 3/10 plus 3/100 plus 3/1000 plus 3/10,000. An infinite series, or simply a series, associated to a sequence A sub n is the sequence of partial sums. Since we think of a series as being an infinite sum, we use these two notations to denote series. The implication is that a series is an infinite sum, but it's really a sequence of partial sums. Let's make 2 remarks. First, when determining whether or not something is a series, it doesn't matter where we start our indexing, so this thing is also a series. Second, the letter used for indexing doesn't matter either, as long as we don't use a letter that's already being used for something else. For example, the sum from n equals 0 to infinity of a sub n equals the sum from I equals 0 to infinity of a sub I, and they're both equal to a sub 0 plus a sub 1 plus a sub 2 and so on. Let's look at 2 examples of series. First, this is an important series called the harmonic series. Written formally as a sequence of partial sums, the series is this. Second, this series is an example of a geometric series, which is a series whose successive terms have a constant ratio. In this case, that ratio is 1/2. Written formally as a sequence of partial sums, the series is this. We've defined a series to be a sequence of partial sums of another sequence. However, the intuition that a series is an infinite sum is so strong that we often speak of the sequence of partial sums associated to a series, even though, formally speaking, the series is the sequence of partial sums. Sometimes a series is defined syntactically as this formal expression, but we haven't taken that approach here. A question naturally arises, namely, when does a series represent a number? Since a series is a sequence, the answer is in terms of sequences. A convergent series is a series whose sequence of partial sums converges. The value of this limit is the value of the series. All other series are divergent. For example, the partial sums of the sum from n equals 1 to infinity of 3 times 10 to the negative n are all of the form 0.333 and so on for some finite number of 3's, and the sequence of these converges to 1/3. As another example, the partial sums of the series 1, -1, +1, -1, +1, and so on are 1, 0, 1, 0, and so on. And this sequence doesn't converge. The series is therefore divergent. One last remark. Just as with any other limits, there are 2 special ways in which series can fail to exist, namely by approaching plus or minus infinity. For example, let's consider the series whose terms are the positive integers in ascending order. Then the limit of the partial sums is the limit of this expression, which diverges to infinity. So this series equals infinity. Strictly speaking, it diverges.